Good day, my name is Martin Schiffner. I'm with the Chair of Medical Engineering at Ruhr University Bochum, and in this presentation I would like to introduce frequency-dependent F-numbers that suppress grating lobes and improve both the signal-to-noise ratio and the lateral resolution in synthetic aperture imaging. At the beginning, I would like to underline the benefits of a technique known as dynamic aperture. I will then review two methods to compute F-numbers, which are important parameters of dynamic apertures, and propose a combination of both methods. Subsequently, I will describe a simple implementation and present experimental results. In the end, I will summarize the most important findings. Let us begin with the motivation. The F-number is an important parameter in synthetic aperture imaging with linear arrays. The full aperture, or no F-number, introduces significant artifacts close to the linear array. The usage of a dynamic aperture with a fixed F-number, in contrast, removes these artifacts. The F-number is defined as the ratio of the focal length ZF and the desired aperture width A of ZF. Two methods have been proposed in the literature to compute F-numbers. The first method uses the signal-to-noise ratio. The elements of the linear array have a directivity that is proportional to a sinc function. This directivity attenuates the signals from the focus. The F-number excludes signals that mainly contain noise. The second method uses the signal-to-interference ratio. The aperture width controls the amplitudes of the grating lobes. The F-number suppresses interference from scatterers away from the focus. Both methods yield similar F-numbers in the range from 1 to 2, but are mutually contradictory. The F-number, moreover, should increase with the frequency. So the research questions are: how does one combine both methods? And is it beneficial to account for the strong frequency dependence? To answer both questions, the influence of the F-number and the frequency on the properties of the pulse echo beam were examined. These properties include the lateral width of the focal point and the grating lobe amplitudes. As the frequency increases, the width of the focal point decreases and the grating lobe amplitudes increase. The same effect can be observed when the F-number decreases. So increasing the frequency or decreasing the F-number decreases the width of the main lobe and increases the grating lobe level. To determine the effects of these relations on synthetic aperture imaging, the pulse echo beams were decomposed into a main lobe and grating lobes. This decomposition enabled computation of the signal and interference powers for each frequency and each F-number. The signal power, assuming a random medium with uncorrelated volume elements, is proportional to the energy of the main lobe. The interference power, in contrast, is proportional to the energy of the grating lobes. To determine the effects of the noise on synthetic aperture imaging, the noise power in the focused signal was estimated. This estimate required the channel noise power, which was assumed to be equal in all channels. The channel noise power for each frequency was estimated as the average energy in the Fourier coefficients of the noise for all channels and all transmit events. The noise power in the focused signal, assuming the noise in separate channels to be uncorrelated, was proportional to the square of the energy in the apodization weights. These considerations enabled computation of the signal-to-interference plus noise ratio, SINR, and proposition of an F-number. The SINR includes the effects of both the interference, which is caused by the grating lobes, and the noise. The SINR, moreover, depends on the scattering power and thus on the object. Two domains can be identified. One domain in the top left corner, where grating lobes are absent and noise dominates, and one domain in the lower right corner, where strong grating lobes occur and interference dominates. Moreover, the decay of the signal power for low frequencies and high frequencies and the effect of the element directivity can be observed. The proposed F numbers are level curves of the normalized SNR for each frequency. These F numbers provide optimal SINR for each frequency. The proposed F numbers are frequency dependent and require a Fourier domain beamforming algorithm. A grid of image voxels and the RF signals for a complete synthetic aperture scan serve as inputs. The algorithm, in a first step, applies the fast Fourier transform to the RF signals to obtain complex-valued phasors for the relevant frequencies. For a selected image voxel, the algorithm then computes frequency-dependent apodization weights, which also include the delays, and multiplies the phasors by these weights to obtain the weighted phasors. The summation of the weighted phasors for all transmit elements and all receive elements then yields the focused signal in the Fourier domain. An inverse FFT provides the focused RF signal in the time domain. A specific sample of the envelope serves as voxel value. The last two steps can also be combined into a three-dimensional sum of the weighted phasors. To validate the proposed F number, an experiment with the Sonics Touch research system and a linear transducer array with 128 elements was conducted. The excitation voltage was a single cycle at 4.5 MHz, and 80 synthetic aperture scans were required to enable computation of the signal-to-noise ratio. The object was a commercial tissue phantom, and the F numbers included the full aperture, a fixed F number, optimal signal-to-interference plus noise ratio, and 90% optimal signal-to-interference plus noise ratio. For the tissue phantom, the usage of the full aperture resulted in grating lobe artifacts close to the array. The signal-to-noise ratio was relatively low, with a median of 18.6 decibels and an interquarter range of 14 decibels. The median width of the wire targets, however, was small and amounted to only 326 micrometers with an interquarter range of 82 micrometers. The fixed F number eliminated the grating lobe artifacts and improved both the contrast and the signal-to-noise ratio, whose median increased to 20.7 decibels. The median width of the wire targets, however, increased significantly to 577 micrometers. The usage of the proposed F number with optimal signal-to-interference plus noise ratio improved the values of both the median wire width and the median signal-to-noise ratio. The usage of the 90% optimal signal-to-interference plus noise ratio further improved both metrics and still suppressed grating lobe artifacts. All F numbers suppress grating lobes and improve the contrast by up to 5%. The proposed F numbers, in comparison to the fixed F number, reduced the median wire widths by up to 21% and improved the median SNR by up to 3%. So in conclusion, a method to determine an F number in synthetic aperture imaging was proposed. This F number optimizes the signal-to-interference plus noise ratio, SINR. The signal and interference powers were obtained from numerical simulations. The noise and the scattering powers were estimated from measurements. A Fourier domain beamforming algorithm accounts for the frequency dependence of the f-number and the apodization weights. Experiments show that the proposed f-numbers, in comparison to fixed f-numbers, improve the lateral resolution by up to 21% and improve the SNR by up to 3%. The proposed f-number and the Fourier domain beamforming algorithm are easy to implement. So the answers to the research questions are: the f-numbers should derive from the signal to interference plus noise ratio, and it is beneficial to account for the frequency dependence. Thank you very much for your attention.